So the first one is by Professor Cyrille Artho from KTH, Sweden. So Cyrille obtained his master and PhD degree from ETH Zurich in 2005, focusing on faults in multi-threaded programs. He worked with the NASA IMS on detecting high-level data races in concurrent software. After completing his PhD, he worked as a postdoc researcher at the National Institute of Informatics in Tokyo, and later as a senior researcher at AIST. Since 2016, he has been an associate professor at KTH Royal Institute of Technology in Stockholm and a member of the KTH Center for Cyber Defense and Information Security. Professor Artho developed the NetL cache and ModBat tools for analyzing concurrency and network programs, with recent works focusing on smart contract analysis and IoT software security. Without further ado, let's welcome Professor Artho.
Not too many microphone changes, I hope. So today I'm going to show you how we can make your smart contracts robust against exploits of their business logic in case it's not fully encoded or programmed correctly. This is collaborative work with many other people, and I'm not going to read all the names, but it is really they who made this happen. So I only had a small part in all of this. So what are smart contracts? I guess everybody knows. We consider them to be programs on a blockchain which implement business processes and execute them by keeping the state of these transactions on the blockchain. And this is maybe something that you can look at in a similar way compared to normal software. Compared to most business software, though, the difference is that the assets are directly impacted by these transactions. And the smart contract is really the only safeguard there. And because a smart contract cannot be changed once deployed, we really have to get it right the first time. And there is a very strong need for effective verification methods here. So it's really the best case for formal or lightweight formal methods to apply on smart contracts. Now, why is it difficult to write robust smart contracts? The problem is that the Ethereum virtual machine, for example, is a very general purpose virtual machine, and it doesn't provide a lot of ways to safeguard your smart contracts in a, say, declarative way. You are responsible for coding the smart contract in the right way, so it checks the user permissions, it makes sure that you're not, say, withdrawing funds that you don't have, etc. So all the responsibility is on the programmer. And of course, we are human, we are not perfect, and mistakes happen, and sometimes these mistakes can be very costly. So depending on the exchange rate, up to $500 million were lost in exploits, and some of them were low-level programming mistakes, but some of them can also be considered logical flaws in the software. And what can we do about this? The solution that I propose today is by leveraging model-based methods to get a strong verification that we can apply throughout the life cycle. So by having a specification of the design, how the different steps in a smart contract interact, we go beyond assertions that only check at certain isolated points in time what happens. And we have something that we could use for static analysis, but also for runtime analysis, in particular when we test a smart contract or when we monitor a deployed smart contract. And for the rest of this presentation, I'm mostly focusing on testing. And where can we position this approach or this type of approach, and why do we choose this as opposed to other methods? In a very simplified way, here we see a pyramid that shows several types of verification approaches they start with methods that are completely automated. They require no human effort whatsoever, but they are also only able to see general problems. And then you go higher up and you gradually get more specific, but you also increase the amount of human effort that you need. So you get more expressive in that way too, and you can verify properties that are closer to the semantics of your code. But of course, there is a bit of work required. And model-based methods, I think, really have this golden balance between a reasonable human effort and scalability by being still somewhat general and applicable to many similar scenarios. So you have a good trade-off between automation and human ingenuity. Now in detail, at the bottom we have, for example, static analysis with fixed rules or fuzzing. You just install the tool, push a button, and you get results. And these tools are good for low-level programming errors, but they are hard to customize. Most of them cannot be customized, and they are limited to such generic properties. One step up, we have unit testing, where the developer typically has to specify examples. This input and this transaction gives me this output. And it's very precise for that, but it's limited to those examples. The model-based methods, they can generalize across many of these examples. So unlike unit testing, they are not limited to one test or two tests, but they are generalizing across thousands or millions of tests. And while at the top of the pyramid we would have mathematical proofs, these proofs are typically very hard to do. They require a huge amount of effort. So I think model-based methods are a good way in between. So the effort is much less than for full formal verification, but sometimes you get quite close to the power of these formal methods. Now, how did we get there? In earlier work, also with Yi and his students, we looked at somewhat general properties that are a step up from low-level programming mistakes. So low-level mistakes would be, for example, overflows of numbers. And that's something that exists in most programming languages, and everybody would agree that that's a bad thing. And it's relatively easy to detect, but there are other errors out there. And some types of flaws, for example, occur if you can exploit the transaction logic so you can take funds out of a somewhat closed ecosystem among the participants of a transaction. And if you describe an oracle in that way, you can then detect if someone tries to siphon off money from a smart contract, and you find those kinds of vulnerabilities. In work after that, we then looked at access permissions. By looking at transactions, we could reverse engineer what the roles are that have the permission to carry out certain operations. And then by testing more possibilities, we could see if the smart contract actually enforces these roles. So we can see that this is a step up from very low-level things. It generalizes to many types of smart contracts, and it does that for two types of behavior. Now, how do we get to a lot of behaviors? How do we generalize further from that? And this is where these model-based methods come into play. So by having a modeling platform, I have an abstraction from the code, so I don't have to write quite at the low level of code, but I also have a way to express things that are quite flexible and really relate to these different steps in a transaction of a smart contract. And by using a monitoring tool, then I can check if the execution of a smart contract conforms to what was specified in the model. And how do we then actually apply this and support application-specific aspects? So the way we do this in this line of work is that we use so-called dynamic condition response, or DCR graphs, to capture the semantics of the smart contracts. These DCR graphs have been widely used in the business process community and have been very successful. And because smart contracts are nothing but codified business processes, they actually are a really good match to smart contracts too. So you can see a small part of a DCR graph on the bottom left. We have a box with the role on the top. So that's exactly what we also use in smart contracts. And then we have the action at the bottom. And each box can be enabled or disabled. So this box is drawn with a solid border, so it's enabled. And each box represents an activity in a smart contract, so a function call typically. And because each function changes the way how the smart contract can work, it changes the state, these activities in the model can enable or disable other activities when they run. So let's look at the more complete example. So this is a very simple model of a bank that can give out a loan to a client, and the client has to pay it back within a certain time. And we can see at the bottom left, we still have the role of the bank that gives a loan, and we have two green outgoing arrows. And each of these arrows points to a dashed box. And this means these dashed activities are disabled when you start, but once the bank has given out the loan, they are enabled. And what happens then is that once the client has received the loan, it is able to pay back interest or the whole loan. And that then has another impact on this last action here. The bank is able to fine a client for not paying back the loan. And we also have red arrows. Those disable other activities. So once the client has paid back the loan, the bank is no longer supposed to fine the client. And once the bank has fined the client, this is not supposed to happen again. So we can disable itself there in the activity or disable other activities. And as it turns out, this is a very, very flexible way of modeling activities, and it maps really well to smart contract code. So here we see an example written in Solidity. The function names, they map to the activities. Require statements either are concerned with a user role, or they can also map to a precondition of these arrows, which are not shown graphically, but you can have require statements sort of embedded there. And we looked at a large number of design patterns of smart contracts, so over 20, and we found that many of them, pretty much about 3/4 of all of them, of the widely used design patterns in literature, they can be expressed very well with these DCR graphs. So this provides us for the first time a formal model of a whole catalog of design patterns for smart contracts. And these design patterns, they have some similarities with Eric Gamma's design patterns for object-oriented software, but they're also different in a way. So traditional design patterns, they are related to the structure of the software, how different components are interacting with each other. Smart contract design patterns are transactional in nature. They describe in what order operations have to happen, and they do not necessarily prescribe the structural relation in many cases. So you get some freedom there. Still, there are a family of structural design patterns. As you can see in this Venn diagram, there is some overlap too. Others directly relate to dependencies between actions or access control. And finally, there are quite a few design patterns that are also temporal in nature, like in the example with the loan. I hadn't mentioned that label on the arrow. You can have a time limit too. So for example, the bank has to wait a month before it's allowed to fine the client for a late repayment, because otherwise there wouldn't be much of a point of the loan if you had to repay it immediately. So with this, we have a powerful family of patterns which are model-based and with the tool that can evaluate it also formally defined, and we can apply these to many types of smart contracts. And to monitor them, Mojtaba, my PhD student, has implemented a tool called HighGuard. So it guards against high-level design violations. And the way it works is that it takes a smart contract with an exploit pattern. So it has a template for an exploit that has, for example, possible sequences of actions and values. And then it monitors the implementation against the model that I showed on the previous slides, or that type of model. Of course, for different design patterns, it's a different set of models. It then captures the actions on the blockchain, translates them to the level of the model, because it's a somewhat different abstraction level there, and then it executes the model itself on this engine for these DCR graphs. And the model then can see if the actions that are incoming are actually permitted according to the model. And if not, then we have a violation of the property, which means that either the model is wrong or that we have a flaw and a successful exploit that we have seen. Now, to see how effective this is, we need a number of exploits and also a number of vulnerable contracts. The problem is that there are not so many annotated examples in literature. So most works, they use static analyzers for low-level programming problems, and the static analyzers are often imprecise. So we needed examples with a reliable ground truth. The way we approached this is that we took a couple of manually verified examples, and we asked ChatGPT to diversify them. So to insert additional similar vulnerabilities or similar flaws, while still keeping the overall behavior in line with the specification that we have. And in this way, we can generate a lot of similar vulnerable contracts, and we can diversify a small data set by a factor of about 25. We then use this tool, so the prompt to ChatGPT, it includes first an explanation of the task. The goal is to diversify one example smart contract and get more and more versions that are similar but vulnerable in slightly different ways. We then provide the semantics of the DCR graphs from a description of the different arrows and boxes. So that part is something that we don't really have to come up with, because that exists already in literature. Then the source code of the contract, the DCR model itself in XML specification. So the summary also provides an explanation of the encoding of the contract of the DCR model. And then a template, how you might go after exploiting it. And then we ask ChatGPT to generate more exploits and still adhering to the overall structure. And it is able to understand that in many cases it produces usable exploits, and those are then the ones that we use. So we start with a bit more than 100 variants, which are also generated with these prompts, and about half of them actually have an exploit that works. So sometimes ChatGPT comes up with code that doesn't really work, and we just ignore that. So we take the remaining 50%. And because we only are interested in successful and complete exploits that violate the business logic, our monitor is actually precise. So we don't get false positives and false negatives. But we are not looking at partial exploits. We could do that too, but only at successful exploits. And in that case, because we are doing this at runtime, we don't have any false positives. And because the design patterns are general enough, we also don't have false negatives. So to conclude, smart contracts, they really embody business processes, but they're hard to implement, so we have to be actually very careful with getting them right for the first time. And a full mathematical proof, for example, with deductive logic, is too expensive typically. So I think model-based methods are a good way in between how we can express critical design patterns and apply them to many smart contracts that use these design patterns. And these models can then be monitored with automated tools. So this can be done in testing, but it can also be done in production. And you could, for example, stop a smart contract if a vulnerability is found in production. So we have ways to safeguard your smart contracts at various stages in the life cycle. And on the right, we see this example with the bank. If you look at the paper, I can give you the link. We have a full catalog online on GitHub with all the design patterns, and also we have a journal paper in progress. And I would like to give special thanks to Moshtaba, who is a final year PhD student. So I expect him to graduate in summer. He has a lot of great ideas and more works in the pipeline about smart contracts. So if you would be interested in hosting a postdoc about a year from now, please let me know. I'm sure he would be happy to have a couple of options. Finally, for the future, a visualization of this behavior of the model alongside the execution is something that we're working on, so that you can really visually match how the code interacts with the execution. This is just a mock-up, so this has just started, but I hope that another time I can show you more detail. So thank you for having me, and I'm happy to answer questions.
Thanks for the great talk. Quick question, maybe I missed something, but I mean, for me, this looks like absolutely making sure that the code has no vulnerabilities. I didn't get the restriction about business logic, in the sense that if you remove that completely from your slides, I would completely buy it as well. So what restricts your work to business logic bugs, and what wouldn't apply to other bugs that we see in standard system security?
Well, we consider this business logic in a wider sense. So, for example, access control or governance or guards, they usually embody business logic. And these DCR graphs, they were designed to capture parts of the business logic that apply to sequences of functions, possible sequences. So they come actually from that community, which I wasn't very familiar with before I started this work. And in this formalism, there is a strong link to the business logic. So for example, if someone who doesn't have access permission can exploit the function to withdraw funds from a smart contract, this can be seen as a business logic exploit. It's a coding exploit that results in the business logic being flawed.
Yeah, I guess I see that. Yeah.
More questions?
I'm just curious, when you are using the ChatGPT to synthesize the new exploit, are you, so how diversified it is? Are you going to just ask it to change some parameter numbers and still have the same exploit, or is like there are control flow path changes? Or so? Just want to know what's limit of GPT synthesis can be done.
I don't remember the exact wording of the prompt, but we don't prescribe overly much how it changes it. So there are a variety of changes, from very local changes to, for example, removing requires, to somewhat larger changes. And then some of them are unsuccessful. So also in the second row, you can see that we were only able to get 4 usable versions out. In the other ones, we could get at least 25, so we stopped at 25. So we give ChatGPT a lot of freedom, and sometimes it works well, occasionally a bit less well.
Okay, let's thank Professor Artho again for the great talk.